Hello, in this video we will be looking at how to find the number of longest increasing subsequence in an input array which is strictly increasing in terms of the sequence. We have an input array, let's say 10, 9, 2, 5, 3, 7. What we have to do is a continuous increasing subsequence needs to be found, something like 2, then 5, and then after 5 we have 3 here, which is less than this previous 5 here. So this is no longer a longest increasing sequence, so then we just skip it and go here, which is greater than 5. So one example can be 2, 3 and 7, and another example can be 2, 5 and 7, because in both cases it's increasing, and in one case we can say it goes from 2 to 5, and then you skip 3 because this is reducing, and then 3 to 7, and in another case we can say 2 to 3, which is also increasing, and 3 to 7. That's the problem statement, and we will be building a solution in JavaScript and also compute the time complexity and space complexity of the solution that we build in this video. We will try to achieve a solution using dynamic programming, and before jumping into the solution aspect of it, let's just first try to understand why we feel that we will be using dynamic programming to reach a solution here. So in this problem statement, it is said that we have to find the longest and strictly increasing subsequence. Whenever we have problem statements that say try to find the longest or the minimum or the maximum, in that cases usually we can use dynamic programming approach and try to reach a solution. What we usually do is try to find a smaller problem statement. In this case, the smaller problem statement will be we have to find increasing subsequence. So we can find smaller increasing subsequences and then combine those smaller subsequences to reach a final solution that we are looking for. So that's why also this makes a very good case for dynamic programming. And usually with this approach, the trickiest part to do is to figure out what is this smallest problem statement that we are trying to solve, after which we will combine those solutions from these smaller subproblems to the final solution that we are looking for. So in this case, the subproblem will be a subsequence which is increasing. It might not be the longest, but it's good enough to just have a smallest subsequence, and we will try to build a solution around this. And the approach we will take is something like this. We will maintain a state of the subsequence solutions that we build, and we will keep updating that state to reach a final solution that we are looking for. And for this state, we usually follow the approach of naming the array as a DP array. So the normal convention is whenever we try to store subproblem states and try to find the bigger solution, it's always a good practice to put it in an array called as TP, and then we have a trigger value. So because we are trying to find the smallest problem subsequence and try to solve it, we need to start at some point, which will be our smallest point. Now we said we are trying to find subsequences, and what a smaller subsequence than having just one element. So let's say we just have one element in this array. What can our longest subsequence can be? It will just be 1, because you can say that if you don't have any other elements and you just have this one element, the sequence will be 1 because there's just one element and it is increasing. If you just have 9, for that also it's same. If you don't have the rest of the elements and you try to say what is our longest subsequence or the subsequence itself, it will just be 1. And similarly, we pre-fill it for the rest of the elements with the presumption that just one element exists in this input array that we have. This becomes our trigger condition. And using this trigger condition, we will now try to combine our subsequences. So we find small subsequences and we club them together. So we might have 2 small subsequences. So this is 1, this is 2. We will combine this 2 and then try to reach a bigger solution that we are looking for. That's the whole approach of dynamic programming which gets applied here, or in general anyways. As long as you can find this pattern that you can solve some sub problems and then reach a bigger solution, only then we apply dynamic programming. Otherwise, this doesn't satisfy the use case of applying dynamic programming. And it's sometimes get quite tricky to find this sub problems. So we have to choose very carefully which approach we try to solve our problem statements in. In this case, it seems fine so far because we found a problem statement saying we will try to find a subsequent solutions. We were able to have a trigger value also. We will maintain this DP array. And then we said we will combine this small subsequences to reach a final solution. Now I will elaborate a bit on this small subsequence thing. What I mean to say by this is, if I have a value of 3 here, let's say, which is here, and if I am able to find before this a sequence of elements which is lower than my current element. So let's say I am able to find 2 which is lower than 3, and if some other lower chain elements which we have, and if I am saying that we are going to be adding this smaller subsequences, if I know the solution of this subsequence. So let's say this was our subsequence because before 3 we have found something which is less than 3, and if I know the solution of this, I can just add 1 to this, which is basically increasing the number of elements in a subsequence by 1, because whatever value had so far until this, you just add 1 to it, and then you get a final solution, which will be 2 here if we just had 2 elements. If I extrapolate this approach, what this will convert to is, I have to find elements which are lower than my current element in my array, and then if the solution exists for my lower elements in the sequence, I just add 1 to it. Or if, let's say, you had just 3, we did not have 2, then it also would have its own solution in the DP array that we are trying to keep here. So this will be a tracker for solutions of our smaller subsequences, and 3 can also have its own subsequence, and we might have come to 3 from somewhere else, let's say maybe from 1 here also. So it might also have had its own solution compiled before trying to compile it for this element. So we will try to, from all these solutions that we might already have, we will just try to get the maximum. So what this will translate into code is something like this. We try to find the maximum between my current element in my DP array. This is my DP array of this element 3, which is at position 0, 1, 2, 3, 4, 5. So dp of 4 of the solution of this one in my dp array. So 0, 1, 2, 3, 4, 5. So this one, comma, if there is a previous subsequence which is lower than my current element, I will just use that one, which in this case was 0, 1, 2. So dp of 2, which is this one, plus 1. So whatever maximum value I get from this 2, I will just try to use that value. So that's the whole concept of the subproblem expression that we are looking for. So if we are able to determine this problem relationship of my repeated subsequence pattern, so if I repeat this number of times enough to reach a solution, then we accept this as our subproblem expression statement. It's a bit tricky to come up with this because we need to find something that will be able to repeat itself until we reach a solution. And yeah, let's try to take this as a base case and try to just solve it before we try to jump into the coding aspect of it. So let's say you have everything initialized here to ones, and because we said if only one element exists, that itself becomes the longest subsequence, which is just 1. I will start with I as 1. Reason being, for the initial element I have already pre-filled with a value of 1, 1, 1, 1 everywhere here. So now I will say make I as 1, and what is the element at position 1? So this is 0, this is position 1. Right now at this position we have 9. So we will say we have 9. Now in this example we mentioned we will try to find something which is smaller than my current element. It has to be smaller because we are saying in the problem statement itself you have to find the longest strictly increasing subsequence. So if you find something that is higher, it is not increasing and not valid solution use case that we are looking for. And we can say something like this. We will say in this array that we have with us, which is 10, 9, 2, 5, 3, 7, just iterate over the entire array and try to find the smaller subsequences. So we will iterate through each element and try to find a subsequence that links to it in the hopes of trying to reach a solution. So we have 9 here. Now we will compare this 9 with 10. Is 10 less than 9? It is not less than 9, and because it is not less than 9, we will just skip it. We are only concerned about values that are less than 9. So we will say skip it, and we will only go up to the element itself. We will not go beyond it, because if up to this point the conditions are not getting satisfied, then there is no point going beyond it. That's why we just stop there. Now I will change my I to 2. So now what we will do is we will make a I as 2. From 1 it becomes 2 now, and at 2 we have this element which is 2. Now I will again iterate through my entire array. So I will say, hey, is 10 less than 2? It is not less than 2. So we will just skip this one. Then we go to 9. We ask, hey, is 9 less than 2? Nope, it is not less than 2. We skip this as well. And then you reached here, so we stop there. Then after this, we increment I again. Now I will become 3. And now we will say the value here is 5. Again, we will iterate through the whole array input that we have. We will say, hey, is this 10 that we have? Basically, the idea is we are trying to find something that is lower than my current number and try to form a pattern of increasing subsequence. If I don't find it, I don't do anything with the iteration that I have. So I will say, hey, is 10 less than my 5 value, which is my current iteration? It isn't. So I will skip that as well. Then the next sequence is this one, which is 9. Hey, is 9 less than 5? It isn't. Then you go to the next element, which is 2. I will say, hey, is 2 less than 5? Now we reach our happy path. Yes, I found a number in the sequence which is lower than my current number, which makes possible case for my increasing subsequence chain. And if I have a solution for this one, I can just add 1 to it, and hopefully it might be a solution, or our current solution might be our best solution that we have. By best solution, I mean the longest number that we are looking for. So if I apply this condition, I can just say max of my current value, which is at iteration 3. And please note that when I say current value, I mean current solution, which usually is going to go in my DP array, where we store the state of our sub-solutions. So I will say max of DP of my current iteration, which is 3, and DP of my number which I found to be lower, which was at index this of 2. So DP of 2 plus 1. If I'm able to find this value which I am looking for, then I can say that, hey, my condition is being met, and then I can just proceed ahead with my condition that I am looking for. So now I will say max between these two is, if I see DP of 3 here, it is 1. So I will just say max of 1 comma DP of 2, which is here, is also 1. So it will be 1 plus 1, and max of 1 comma 2 is 2. So I can say that DP of 3, the new DP, so we started with initial trigger value for this one, and what I can say is for this 3 value, which is holding the element 5, I can just now update this to 2 from this iteration that we saw. And this is the base of our problem statement. We will just keep repeating this throughout our array input that we have, and at the end we will reach a solution in this DP array. So somewhere in the DP array we will have a solution, and then from that solution we will extract the highest number. Now we were able to find the numbers, we just don't know yet whether it's the highest number or not. And this will translate into code something like this. So what we said is that we will be having a DP array here that we looked at, which we initialize to once. So I will just say let DP is equal to new array of nums.length. It will be equal to the length of elements we have, because for our trigger condition we said if you just have one element, the length itself is 1, and we will say fill it with 1 based on the statement of pre-filling with 1. And then we said we will keep iterating through all the elements that we have, and that will just look something like this. Nums.length, I will have a loop here. Now you see here I have initialized I to 1 and not 0. Reason being that I have already pre-filled my array with ones. So the 0th case I already manually found the solution and pre-filled it here. So that's why I'm just starting with 1, and then I will have to iterate through all my elements which we saw here. So we were just incrementing our I and trying to go from the first up to the ith element, trying to find a lower number than my current number which I had. So I will say use j, and j will be less than I. So I will only try to go up to my element, because if it is beyond and you have not yet found the lower number, it's no point trying to find this smaller subsequence pattern that we're trying to say, that find something that is lower than your current element, and then whatever the solution of that lower number is, just add 1 to it to reach your new solution at your current element. So I will just loop through this, and this is our mechanism that we talked about to iterate. And now comes the main component of this, wherein we said that, hey, if you are able to find a number which is less than my current number, so if nums of I am inside this iteration, so j is less than my nums of I, which is my initial number which I pick up in this iteration. If I'm able to find a lower number in the previous elements that I have, then what I do is dp of my current element is going to be math.max of two possible cases. Either I can have the solution in my current element itself as the maximum solution if I have pre-compiled it from some other path, because in the original problem we saw we can have more than one solutions, or it will be dp of j, which is a previous element. So in this case we said this was our previous element, and similarly here we found the previous element and then added 1 to it. So that will be just dp of j plus 1, and whatever is the maximum I will put in my dp of I. And that's pretty much it in terms of the logic we covered so far, and we will pre-fill it with the solutions inside this dp array. We will not have a continuous sequence such that if the last element whatever you get is going to be your highest, then from this we are going to be trying to find the longest number that we have. So I will say max is 0, and I will be returning my max in the end, and I will say for my current value of my dp array, I will say max is going to be math.max of current comma max. So I will just find my highest value which I am looking for once I reach my solution in my dp array. So my dp array will have solutions to smaller sub problems by the time we complete this mechanism, and that's where we reach our solution. Now in terms of time complexity, we have two nested loops here. One goes from the first level for the entire subarray, and then inside that up to that element we go in another loop. So this will be time complexity of order of n here, and then worst case we can go up to the last element. So if we combine these two, the final time complexity of our solution will be order of n square. And in terms of space complexity, it will be order of n, because this nesting is going to store an array of dp solutions, and it will depend on our length of nums. So based on the length, the store of the array will vary. That's why we said space complexity will be order of n. It's not going to be constant. That's the whole concept which we wanted to look at, and now that's pretty much it. We can also try to dive deeper into it and try to correlate this code to our initial problem statement that we had. So what I will now try to do is, let's just try to relate to this and link the code that we solved to our problem statement which we had originally, because I understand that this DP solutions can be a bit tricky to get a grasp on. So it's always good to first cover the concept, then cover the code aspect of it, which we have covered here, and then just try to link both of them together before wrapping everything up. This is our final solution. You can choose to just skip the video from this point, because we computed the space complexity, time complexity, and also the main sub-problem aspect of it that we're looking for. Now I will just go manually over the sequence to hopefully explain it a bit better to our viewers. So what we will do is, let's say we have input as this one, we have our DP array which we said we have here, which is 1 1 1 1 1 and 1, which we initialize. So 0 1 2 3 4 5, 0 1 2 3 4 and 5. This was our input. I initialize everything as per this statement, filled with 1, and then I will start with I is equal to 1, which is going to be element 9 here. In this case, I will say, okay, my pointer is at 9 right now. I will try to find within this nested loop from 0 up to this element. If I find something which is lower than my current element, I find 10 here at 0th index. Is 10 less than 9? It isn't. So it's not a valid use case. Then that's pretty much it. We end here. Then I go to I is equal to 2, which is here now. So now I will go from here to this one, and the value there is 2, which we have there in terms of the current pointer, which is at index of 2, and this was index of 1 that we had. Now I will again go from 0 up to this point to try to find my solution. I will say, hey, is 10 less than 2? No, it isn't. Then I will go to the next one. I get 9 here. Hey, is 9 less than 2? It isn't. Then I reach here, I break. That's it. I don't proceed any further. Then I becomes 3. At this position, we now have I, which is at 3, which is 5. The value of the element is 5. We will again start the whole thing again. We will say, hey, is 10 less than 5? No, it isn't. Hey, is 9 less than 5? Hey, it isn't. Is 2 less than 5? Yes, 2 is less than 5. So we found our happy path scenario, which satisfies our condition of this nums of j is less than nums of I. And now what we will do is dp of I. So dp of I, which is here, I is 3 currently, is going to be max of dp of I itself, which is max of 1 comma. I try to find the dp of j, and the j at which I found is here. So this was j is equal to 0, j is equal to 1, and j is equal to 2. So at position 2 I found it. So now position 2 we have 1, so it will be 1, and then I try to add 1 to it because I found a lower element. Whatever the maximum of this 2, which is 1 comma 2, which is 2, gets replaced here now. So we have here 2 now instead of the initial 1 trigger value which we had kept. Now after this, what we will do is we will go to our next iteration. We will say I is equal to 4. So this will go from here now to here. My value is 3. I will again try to find my sequence. Hey, is 10 less than 3? It isn't. Hey, is 9 less than 3? It isn't. Hey, is 2 less than 3? It is less than 3. Now because 2 is less than 3, what I will do is, and j was 0, j was 1, j was 2 here, I will again say max of my current value. So current value is 1 at this position because my iteration I is at 4, and here I will say that find the maximum from 1 comma the previous value, which is the previous value j is equal to 2, which is this one, 1 plus 1. So here also I will get 2 here, and at this position I can say this becomes 2 now. Now I will move towards the next iteration which we are looking for, and that is going to be something like this. So we will have I is equal to 5, and we will again go from start to the end again and up to this position. So now the index will shift to this position. Now I will come here, so 0 1 2 3 4 5, and I will say, hey, is 10 less than my current value here, which is 7? It isn't. Hey, is 9 less than 7? It isn't. Hey, is 2 less than 7? It is less than 7. So I will say max is going to be my current value at this index, which is going to be 1, and this index was 2. So j is equal to 2 at this point. So 1 2 1, so 0 1 2 for j, and j of 2, which is this one, is 1 plus 1. So we will have max of this 2 is 2, and this will become 2 now. Then we just keep going ahead within the same iteration. So we found 5. Hey, is 5 less than 7? 5 is also less than 7. And then we will say max of my current value. My current value is 2, which was precompiled from this iteration. So we will say 2 comma whatever the value is at this element that we are looking for. The 5 was at position of 3, and at this position we had 2 here. So we will just say max of 2 comma 2 plus 1, which is going to be, this is going to be 3, and then max is going to be 3. So now from 2 it's going to become 3, and then we just move ahead again. We will say, hey, is the next element, which is 3, less than 7? 3 is also less than 7. We will also try to find the max now from my current max, which is precompiled here as 3, and the iteration here is j is equal to 4 in my current iteration, and at j is equal to 4 we have 2 and plus 1, and this becomes 3. So max of 3 and 3 is 3, and then we reach the element in the iteration 7. So we stop here, and as you can see, in the end what I am left with is this array which has the elements which I was saying going to store the sub-solution. So these are subsequence solutions giving the highest longest increasing subsequences, and the increasing part comes from this check that we have here saying, hey, the current element has to be less than my iteration element that I am looking for. So in this case it was like 2 less than 7, 5 less than 7, 3 less than 7, and from this array then I try to find the longest value, and to do that I just use like a iteration here which will say max is going to be math.max of current comma max, and the maximum value is going to be something like this. So you say max is equal to 0 at the start, and then we will say max becomes 1 because we said it's going to be max of current and max. So now it just goes this one, then also it becomes 1, it goes here, it is still 1, it goes here, now max becomes 2, now max becomes 2, now max becomes still 2, then max becomes 3 because current was 2 and this one is became the max here, and then you came here and said math.max of current comma max. The previous max was 2 and current is 3, and 3 is higher, so the new max is 3 and then the iteration ends. And this is our final solution that we were looking for, which is going to be the number of longest increasing subsequences. And that pretty much wraps up our solution. I hope you liked the video. Please like and subscribe. Thank you for watching.